The floor is. So before we start to discuss the possible large-scale facilities, let us start the discussion of today's talks. So I see from the first talks, Richard, of course, he is probably asleep now. So for questions to him, we have to post tomorrow or discuss tomorrow morning. And Geraldine doesn't seem to be around, but still we had all the theoretical, the experimental proposals, solid state and the other proposals. So are there questions, or did something came up in your mind during the short break? So we saw this. So the last talk, it was theoretical. The first and the last were and then not the last, the next to last. So the first two, they were still completely theoretical in a sense, but very interesting.
Well, I see that Camilo has a hand up. I don't know if you see that.
Okay, Camilo.
Yes, I have a question for Juan.
Go ahead.
Yes, so it's concerning this hyperbolic emission of gravitational waves. Can you again show the slide where you have the characteristic amplitude as a function of the impact parameter?
Yeah. Let me go to it before. Okay. So I'll share the screen, if I may. Okay. So you see there.
Yes.
The actual parameters, no, essentially the impact parameter, masses, and the asymptotic velocity. And then the power and the amplitude can be derived from the emission of gravitational waves through the close encounter. And it has maximum strain and maximum frequency given by this expression. So you might have events that are very near parabolic, E = 1, which would enhance the amplitude. Okay, so out of the full distribution, this is part of the discussion that Valerie started in Mattermost, out of full distribution of a localization of black holes, of those masses within clusters, there is a non-negligible fraction which is very near parabolic. Those that are elliptical just simply get bounded and eventually merge if they're not disrupted by three-body interactions and break up. But there are some which can have a large impact. Now, I used the relation between E²-1 and the masses and velocities to write the frequency, which is what you were asking, in terms of the masses and the velocity.
Yeah, so my question here actually is very concrete, because it seems to me that you take the impact parameter as a free parameter, right? But
it's related to the eccentricity, yeah.
Well, but I would naively think that I mean, the impact parameter is related to the cross section, which in turn is, of course, proportional to the masses and the G Newton for a given process, right?
That's for you to get bounded. You could have any impact.
No, just to get the scattering. Even if it, I'm not talking about the cross section for binding the object. I'm just talking about the scattering cross section, like Rudolph for scattering, right? So the impact parameter is not a free parameter. It's not just given by the interspace distance. It is given by the.
No, it depends on the mass of the object. Yeah.
Yeah, but it also depends on G Newton. So if G Newton was 0,
yeah,
it doesn't matter what the impact parameter is. There will be no scattering.
Yeah.
Right?
You can see that if you want on the expression in the slide now. You have a mass, you have a velocity, and your impact parameter, you can write it in terms of your eccentricity. You can just put it anywhere you want. Sure. It just means that whatever your impact parameter, your eccentricity will be a derived quantity, or just the opposite. You get your eccentricity from the impact parameter. That formula holds.
Yeah, so again, my question is, what is the equivalent of the Rutherford formula here for the scattering? So there should be like, I mean, because it's the same thing, right? It's 1 over R, and a 1 over R potential. So there should be like a formula that tells you the impact parameter is given by.
You mean for gravitational Bremsstrahlung?
Yes,
yes. Yeah. There is indeed a formula. That's where you get the actual intensity of the wave, the power of the wave from the equivalent. The only difference is that in the case of Rutherford scattering, you would have through very near interactions of charged particles, you would have a very localized, so 1 over gamma, emission of electromagnetic waves, right? In the case of gravitational waves, the gravitational wave emission is much more broad. If you want, its emission is not collimated. Okay, it's very broad. That's the only difference, because instead of 1 over sine to the square, I think theta is 1 over sine to the 4.
So you had a slide with the H versus the impact parameter, right? And then there were some, not this one, I think afterwards.
Well, in some way, H, the strain, is related to the impact parameter through a complicated function of G.
Yeah, I know, but you had like regions on this plane. So can you?
Ah, yes, this one.
Yeah, exactly. So what is this green area?
Oh, this is the area for which you would get from megahertz to gigahertz frequencies on the hyperbolic encounters. Yeah. Between this range of distances, you get the right frequency for these detectors. If you are at larger distances, the frequency is well below. So it's more into the LIGO, LISA range.
You could also now, if you would now think about Alps would be in terahertz, then you should go to the left. Okay, yeah.
Yeah, you go much further to the left, indeed.
Yeah, yep. Okay. But would this be also of interest?
Well, the range of interest that we're discussing here was between megahertz and gigahertz. So we're talking about 10 to minus 9 astronomical units. So we're talking about less than a kilometer, but of course these are 10 to minus 4 solar masses, right? So we're talking about sizes of those black holes, which are, I mean, tiny, microscopic.
Okay.
So still the distance between those two is large.
Yeah.
We still have hyperbolic encounters. We don't have mergers. Yeah.
So I saw before a hand.
Yeah, it was my hand, but
Eugene.
Yeah, sorry, it was my hi Juan. So nice talk, but
thank you.
I'll ask you the questions now instead of this now. I put out my hand because I have a question, but now I think I might have figured it out myself. But maybe I'll just ask one anyway. So Juan, would this actually generate lots of gravitational memory because you're throwing a lot of mass into infinity?
That's right.
So I would figure that, I mean, naively, I thought they would generate lots of memory because, you know, you're sending stuff to infinity. So you're no longer asymptotically flat, your space-time. But then,
okay, you know that memory goes to zero if you have very large eccentricities, of course, and it goes to zero if you have large parabolic encounters. So there are many of these parabolic encounters. E equals 1 doesn't produce any memory. E equals infinity doesn't produce any memory either.
I think that's right, because your stuff, your incoming is also coming from infinity, I suppose. So that's why you sort of cancels out.
Yeah, that's
okay. Yeah, no, I was about to ask, but then realized, okay, wait.
It's a good question. It's a good question. Yeah, because indeed there is gravitational memory.
Okay, thanks a lot.
I think Valerie had a very nice question in Mattermost, which I'm happy to go into if she wants to phrase it here. Valerie, do you want to go?
Yes, yeah. So my question was about when you showed us these formulas, right, where you essentially get the amplitude right here. So the amplitude, right, or the power for a black hole with a given mass at a given distance. So now if I actually kind of want to make an estimate if any given detector can actually see that, I need to kind of now know what is the observational volume that I actually have, so like in terms of astronomical units like megaparsec or something, that I actually have an order 1 probability of actually such an event happening, right? Because otherwise my detector will likely not see something. And yeah, I saw your answer in Modernmost, right? So that it boils down to the clustering, right? But now, of course, you know, or you and I know that this is a bit of a controversial subject, right?
Well, it's not controversial, it's still explored. I would say it's unexplored. We have a lot to learn about clustering of primordial black holes, because we know that there are some issues we had not developed in the initial picture, which had to do with the quantum diffusion affecting the correlation function. So how often would they find each other near each other to form a cluster? And this depends very strongly on this quantum diffusion providing exponential tails, which means not only that it increases the probability of collapse, and by the way, quantum diffusion, at least for this scenario of fluctuations coming from inflation, it's inevitable, it's there, even if you don't want it. So these tails are going to appear, and they affect on how close to each other those black holes will be when they form. So there's plenty of time from, say, the epoch of electroweak scale, you know, for 10 to the minus 5 solar mass black holes, for them to form before matter radiation equality, and then to evolve as a cluster. Now, we did some simulation, and it's a difficult issue. I agree, and the question is very pertinent, which is to know not only how many pockets of these black holes do we have in our halo. That's fine. That you can do by assuming that these pockets are uniformly distributed in the halo, and you can ask what would be the typical distance between them according to the rotation curves of galaxies and the density of dark matter around us. That's okay. This is what is in the slide that I showed. But then another issue is how compact those clusters are, and whether there's any chance that two black holes would be sufficiently near each other to form pairs and eventually merge within the edge of the universe. You know that the merger rate is proportional to the 4th power of the semi-major axis and to the 7/2 power of the eccentricity, e squared minus 1. So if you have a very near parabolic, or you have a very tiny distance between them, so very compact regions, then you enhance the probability of having mergers soon enough. But the difficulty doesn't come from there. The difficulty comes from the fact, and I'll show you a nice simulation, if I can share the screen, where we did with Manuel Trasorras Sabas-Neseris some simulation of clusters with thousands or millions of objects, and these were for large, massive, and the distances would be typically hundreds of parsecs, but you can imagine the same with much smaller masses and distances of order milliparsecs, so solar system. So let me do the evolution of this, and you will see that you first form, you see the circles over objects. These are binaries. So what happens is that they find each other and they merge, but soon after, a third body will break the binary. That means that you're not going to see the merger, the final merger. You're going to see the churn. It just simply, they're orbiting each other, they become bounded because it's a very dense system, but then another guy comes along and breaks the binary. Okay. Now, it is possible that in the next simulation, some of these get slingshot out. You see this one, we trace this one. Okay. So this one, what it does is that it forms a binary, but this 3-body interactions takes away the center of mass of the system. So it's the whole binary which leaves the cluster, and eventually they merge. Okay.
Okay. So if I
within these
understand
simulations,
correctly,
you have to compute the probability of these events to happen, and that's the thing which you asked for.
Right. So I think there's two issues, right? So one is kind of the primordial clustering, right, which is an open question. Yeah. And then kind of the second challenge is, okay, actually say we have the primordial clustering. Okay, then what is the evolution and what is the probability of finding a binary and finding a binary with the right parameters, right? So I guess it's two difficult questions which need to be answered.
Yeah,
and which we probably don't have the answers to before one can actually make a really solid statement about okay, so you can do kind of a simple estimate based on just kind of whatever homogeneous distribution or something, right? Then of course you come out with a super tiny number. But yeah, I see your point. Okay.
There's the clustering, which I agree with you totally. It's an unresolved question for the moment, but we're working hard on it. It's a tough one.
Eugene, you raised your hand.
Hi, I'm back.
Yeah.
I'm back with the question that I asked just now, because I thought a little bit more about it. And so if you have hyperbolic encounters of spinning black holes, right?
Yeah.
So we know that there's one thing that, you know, that people have used the rotation of Jupiter to use it as a slingshot to accelerate spacecraft, right?
Yeah.
So in a way, you can, if you have hyperbolic encounter, you can sort of extract angular momentum from the black hole. Can you actually do that then? In that sense,
it's a beautiful question.
Your incoming velocity will be more than your outgoing velocity.
Yeah.
You actually have memory.
We have done this kind of a computation with the Einstein toolkit with my student Santiago Jaraba. It's a published paper from this year. And what we find is something very interesting. Indeed, just like there is magnetic induction through a current, there is spin induction. Okay? So if you want the rotation of the system of reference, and among others, it's just simply the black hole starts spinning. If you have a matter current, that is what another black hole coming by nearby would induce a matter current, which would spin up the other one through the usual frame dragging. So we have found that if you do this kind of hyperbolic encounters, we can spin up the most massive of the pair. So actually what happens is that if they equal mass, they spin up, but not much. If they have unequal masses, so you have one much more massive, the one less massive, then there is an enhancement of the spin of the most massive. So there's a natural segregation. If these black holes, primordially, this is valid for any mass. This could be even the LIGO masses, no? So there's a segregation in spin according to mass. And this is something which, by the way, has been observed in some of the LIGO events. So some of the most massive are more spinning than the others. They could be primordial black holes from encounters in dense clusters. So that's an interesting and intriguing idea.
Yeah, I'm thinking of spin down actually, so that your incoming your orbital angular momentum is anti-parallel to the spin.
If the motion is just opposite, so we are thinking that this didn't have any spin and we just had a matter current. This spins up in this direction, right? In the plane of the collision, okay, just as it frame drags space-time around the black hole. Now, of course, you could have it just opposite. So it would be moving against the spin of this black hole, and they would just spin it down. You're right. Okay. Right? So you can do that. You can spin down if the collision happens to lie in the opposite direction. So instead of going up, it's down.
Yeah, actually, no. I mean, maybe I should let other people ask questions. But I mean, I'm just now. This is people must have thought about this, right? So can we do Penrose process instead of with dictionaries with black holes, right? Throwing black holes into an ergo region and see what we get. I mean, have people done that numerically?
I don't know. That's a good question. I don't know. Okay. I haven't tried.
I should stop talking. So thanks a lot. It's really very interesting.
Thank you. Will, you had a question.
Hi everyone. I have a question. I apologize to backtrack. I have a question for Juan and Eugene, as I overheard you guys discussing it really briefly. So we recently myself, Mike Tobar, and Maxime published some results on our high frequency gravitational wave detector based upon the quartz crystal. And one of the comments we received pretty early on was to do with this gravitational wave memory effect, and that in that any high frequency gravitational wave signal would have a detectable trace in the LIGO Virgo band, and it was quite a strong criticism early on. I just wanted to know whether you guys had any thoughts on that.
Oh yeah, I have
basically they said absolutely any signal coming from PBH mergers or anything in the megahertz to gigahertz band would be detectable in LIGO Virgo, is what the criticism was.
I'm afraid not. Actually, I computed what was the amplitude of the memory effect in LIGO, and it's well within noise. So you're not going to see any deviation. Remember what memory effect is. You have this wave, which is oscillating, then you have the merger, so there's a chirp. And then afterwards, rather than being along the same axis of the incoming in frequency, as a function of time, you would see that there's an offset. And this offset, with respect to the incoming one, should be sufficiently large in order to see within the noise, because there's a lot of noise there. Now, you see that the deviation is so small that you're not going to see anything in the LIGO band. And I discussed this with some of the colleagues. I'm a member of LIGO Virgo, and there's no chance we'll see the.
Yeah, I thought.
But this will depend on the magnitude of the signal.
Yeah,
of course, yeah.
Of course.
Sorry. Yeah, I guess I thought it's not the amplitude actually. I mean, the amplitude is fairly big, even for gravitational, just standard primordial
power.
Just black hole mergers. it is the fact that the frequency of is basically a very long wavelength mode. You know, in this memory, it's a very, very long wavelength mode. So it is not within the, if you have a very, you know, even LIGO or LISA, right? They have a fairly long wavelength mode, but your K is basically going to 0. So you can't really observe it. In fact, what people do is just filter it out. That's what people do in observatories. So I guess for high frequency, if you have ultra high frequency detectors, you're even less likely to observe it, because then your frequency, your sensitive frequency is even higher. I guess that is basically, maybe it's that.
Yeah, well, the issue was more along the lines of why bother, you know, any signal you find in this kind of megahertz area. If you do find a signal at all, it should have already been confirmed by LIGO, Virgo.
No chance.
Or any detector at a lower frequency, which I mean,
yeah, no, I don't think
at the time we waved it away, but hearing you guys talk about the memory effect has kind of rejogged my memory.
Actually, I'm interested in what you said at the beginning. So you already have a crystal detector. So I'm losing my time.
Yeah, so this has been published
I'm sorry. Yeah,
in July this year.
I should have known. We were thinking of this 10 years ago, and we never got to publish.
The proposal is in
the chat, the archive number. I'll look for it.
Yep, yeah, absolutely. I'll put it in the Mattermost.
Yep. So maybe I don't have to publish my paper.
Tomorrow we will have a talk by Mike Tobar about it.
Great.
Yeah, he will talk about it on Friday.
Wonderful.
Okay,
wonderful.
very good.
Can I get back to Will's question, because I actually don't think it wasn't at least answered to me, because I think the point is, and I have no opinion on this because I know too little about the memory effect, but I think if I understood Will correctly, the question is, if you had a signal at the frequencies that they measure and at the amplitude that they are sensitive to, right, which is a very, very large signal at high frequencies, would such a signal not leave a trace memory effect in LIGO?
I don't think so. As I said, if you compute what is
does
the
it not
actual
depend on the amplitude of the signal?
Exactly.
Right. It's much more than 10 to the minus 21.
No, but you have to, in order to answer that question, you need to first know what is the signal strength that could be observed in Will's detector, right? Otherwise, we cannot answer the question.
Sure, but I'm telling you, you're not going to see any signal which is smaller than 10 to the minus 21 on those frequencies.
Right, but now the question is, what is the sensitivity of the detector? And if the sensitivity of the detector, I mean, we need to compare the sensitivity of both detector, right, to make a statement. Otherwise, we cannot do it.
But I understand you're comparing with gigahertz, right? So you are saying kilohertz, gigahertz, and you have a memory effect. And you ask, if I would measure anything at the gigahertz, shouldn't I have seen it already at kilohertz? That's the question, no?
Yeah, that one. Yeah.
And the answer is no. It would have to be so big at the gigahertz, probably above BBN bound, in order to see with the sensitivity we have in LIGO, Virgo at kilohertz.
Oh, but the sensitivity that they have is way above the BBN bound. We're nowhere close to the BBN bound. This is the
gigahertz.
At gigahertz.
Yeah. So this is then only an argument because the detector at the beginning is not sensitive enough. So I mean, it's true. Most of the limits which are made, they are in the region where there should be no gravitational waves. So the ones.
By the way, you always do the locking. Okay, even if you had a gravitational wave going through, you would do the locking of the laser in LIGO Virgo such that you erase that effect. So it's only when another gravitational wave passes by that it would induce possibly a memory effect and leave a different offset. Every time you lock the system, you get rid of it.
So I think we could rephrase the question, right? We could essentially ask the question, given that we have given that we want the memory effect to be below the noise curve at LIGO, what is kind of the sensitivity that we need to reach at gigahertz to actually have discovery space, right? So even if we're above the BBN bound, but there's kind of an additional constraint at gigahertz, right? For example, which comes from this effect, right? And I think it would be actually interesting to compute that number. I don't know if it can be done in a model independent way.
So that would actually be a design parameter of every single experiment that wishes to operate at higher frequencies than LIGO Virgo. You have to be X sensitive.
Right.
Yeah, because for them it's the infrared. No, that's what they say. It's a long wavelength. Right. I don't know.
Okay. So maybe we have now to switch to the discussion about the large scale facilities. And tomorrow morning there's another chance to discuss things here about the talks having taken place today. So the idea is now to talk about the experimental prospects and the roadmaps. Now, in this case, for experiments using equipment or having to use equipment which is typically there in large accelerator facilities, so like big dipole magnets and the like, or superconducting radio frequency cavities and so on. And so we had heard talks about magnetic conversion yesterday, experimental talks by Axel and by Aldo, and also about the enhanced magnetic conversion by Woods, Clive, and so the question is now, so how can we proceed in this thing? So the first thing, of course, is with the light shining through a wall experiments and the helioscopes, because they are already looking, so to say, for conversion signals. So the ones from Earth-made conversion, and the others from solar sources, but just the detector or the regeneration side can already be used just as a detector, and from their normal use, you can, as has been shown by Aldo and Hartmut and collaborator and Mike, you can already recast just the data which they have taken in order to a limit on gravitational waves, on at least to gravitational to stochastic gravitational waves. And but the question is, of course, now what can be done with dedicated experiments? And what could be the timeline for dedicated experiments for the Gaussian beams enhanced thing? There has been even not a demonstrator or any prototype being developed. So there is still a lot to do if one wants to really to proceed and to go to beat the BBN bound for stochastic backgrounds and so on. So Axel has already mentioned a possible timeline for how it could go, at least with Alps. So there's the question. The helioscopes like Baby AXO and IAXO and others, they have still at the moment they have had no plan to use one of their things for dedicated runs. So what could be the roadmap or timeline? What do you think, Axel?
Thanks, Andreas. Maybe just a few thoughts. So we have to look for dedicated experiments, like the dedicated usage of the ALPS-2 magnet string, let's say from 2028 onwards. But there could be also smaller, quicker things. Let me just give an example. If you look for axion search, for axion reconversion ALPS-2, we also suffer backgrounds on, for example, kind of photon bursts. So counting, let's say, 2 photons per hour, this would be a burst somehow for us. We would veto. But probably that's nonsense. We should take the data and maybe it's gravitational wave signal, which comes in time. So just the discussion we are having now might be important for the data acquisition in ALPS-2. And another example, also maybe short-term, is baby JAXO is the big magnet with X-ray telescope at the other ends to focus down the axion reconverted photons, X-rays or solar axions down to the detectors. There's the other end of the magnets, which is presently not equipped with any detector.
Yeah, yeah.
So you could think of, for example, having there some microwave antennas.
Yeah.
And just take data parasitically while baby JAXO is looking for solar axions. And maybe we can have this more short-term goals also and maybe look for options for short-term goals where we can just start the experimental field, although surely sensitivities will be limited.
I think so. That are two very good points. So that, yeah, so there has not been, or we did not think about transient. So the detection of transient things with magnetic conversion detectors.
Yeah,
I think this is an interesting question. Of course, one has to have something which can really has a good time resolution and so on. I think this is also a thing to think about. And to this end, of course, and it would be a pity if we lose, so to say, if we lose the possibility to look for transient signals just because we are throwing away the data which we could have also collected all the time. So yes.
So yeah, but as we discussed briefly yesterday, so if with the antenna pattern of ALPS 2 and the motion of Earth daily and yearly, maybe there's an interesting thing we could explore, like certain black holes being dark matter of our Milky Way. And if there were such a case, we can just piggyback it on the normal analysis. But this would raise interest in the community. We can publish some experimental results, and this would pave the road to dedicated usage later.
Yes, yeah. That's
I find that extremely interesting, Axel. Yes, definitely that's worth pursuing. Yeah. So meeting both ends, theorist and experimental.
Yeah.
Let's keep up the discussion. I agree.
So there was one. So Diego and Raffaele, they will only talk tomorrow about superconducting radio frequency possibilities, and this typically is also doesn't sound like a university project. It also sounds like more like a projects for labs, accelerator labs, so could one of you say a few words about what is the status? What are the contacts in the labs? So at DESY, there's at the moment in this connection only an internal discussion, but I heard that in other labs there are already the machine divisions, they are already involved in discussions.
Maybe
so either Raffaele or Diego.
Yeah, I think it's better that Raffaele continue the business.
I take the question. Well, it's the status is a bit fluid at the moment in the sense that we propose to look for axions in a similar way. So
yes.
That case, the theory papers for that already have been out there for a couple of years, and now we have money from SLAC to build a prototype for that. And in principle, it should be realized as a Cern/SLAC collaboration. So Cern will build and possibly coat the cavity with niobium, and SLAC will operate it and design it mostly. This for the axion. So for the same idea for the gravity waves, we are finishing now the theory work. So it's at an even earlier stage, and I think that there are people at Fermilab that are interested. So some of our collaborators are involved in dark SRF and more in general in the Fermilab initiative for this kind of ideas. But there is no commitment at the moment. There is no experimental collaboration yet. So it's really up for grabs. But a lot of the experimental results that we will need will be already coming from the Axion prototype. And that one is already founded, and the expected timeline is a couple of years. For
a couple of years, okay, that's interesting.
Yeah.
Yeah.
So in principle, after these 2 years, we're gonna have we expect to have already some sensitivity to a lot of Axion parameter space, not all the way to the QCD line, and all the noise measurements that will be relevant also for the gravity waves. But there is no roadmap for the same cavity for gravity waves. In principle, I mean, the Mago cavity exists. We found it. It's in some museum in Genova. So in principle, if there is someone interested as a very low cost project, one could recover the cavity, plug it into a power outlet, and do some noise measurements, background measurements, and even some preliminary gravity wave measurements, which would be for, I think, in the 10 kilohertz range, maybe between 10 and 20 kilohertz for the frequency.
Yeah. Okay. That sounds interesting. So and probably so I have seen the SRF cavities have also entered somehow the physics beyond colliders workshop series at Cern. Maybe there should be. Maybe also the gravitational wave things should be also be so at least the ones where one can do the physics beyond colliders with accelerator equipment should be also getting involved. Or we should also contact the PBC in this respect if we have some proposals and so on, because I mean it was also for our Axion experiments. We are already involved in this in the PBC, but I didn't see gravitational waves yet, or ultra high frequency gravitational waves featured in the PBC.
This proposal that Raffaele was mentioned, it was proposed by CERN people, like Picasso.
Okay.
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 But Diego means the original one, the one.
The original one.
Yeah. Okay. No, but so here it was also in this context, of course, but we will be also tomorrow talking about this. So what can be done? So I think also it would be also of interest for us whether people would find it useful to have a hub, so to say, also for gravitational wave experiments, or would they still think, okay, the people at these accelerator labs, they should do it, and we do our small scale experiments. And so the question is there a community forming which wants to wants to build something larger to reach, or I think in the Axion community, of course, it was good to have this many. So it was flourishing in the last decade or so. There were many new proposals for different waves, and in a similar, we are at the moment in a similar mood, so to say. But sometimes then, of course, one has to, if one has identified something, one has to focus on that. So this was, for example, with this abracadabra and these other things in gravitational waves. And now they are focused. They said, okay, this seems to be a good way, but now we do a big consortium. And now they have for many institutes, they have built a big consortium to look into that. And of course, probably, as Mike said, so if we want to have if we want to really go deeply down to the nucleosynthesis bound, then we need some conversion, so hundreds of kilometer long thing with huge magnets, and probably nowadays that's we don't have the energy and all that. So there are so many people have raised their hands. Should I we just start from the left? So Will had something to say. Will, you raise your hand?
No, that must have been a mistake.
Okay, but Nancy, did you?
Oh, sorry, that was also on the previous topic. Let me lower it.
But I guess so. It's still the mic is still it's down.
Hi, yeah. Well, this was an issue that Nancy raised yesterday, but follow on from what Axel said in terms of getting some, well, not just getting some quick results from ALPS-2 in the gravitational wave sector, but really using that as a facility, which is going to be very interesting, I think, and certainly I would encourage people to try and plan to overlap with the operational periods on LIGO, Virgo, and CAGRA, and all these others, because in my mind, there's a really interesting experiment to do to correlate transient events at these very high frequencies with low frequency black hole mergers to test some of these higher dimensional gravities. And I think that's that's really exciting thing to do, and ALPS-2 is going to be there to do it. So it would be very nice to have some discussions about the data formats and exactly how the data was going to be collected and so on and so forth, and other people trying to contribute to help ALPS-2 make a really interesting measurement. So
good. Aldo?
Yeah, I have a technical question, maybe for the theoretical committee. As you may know, in ALPS, they use the cavities, they use cavity for different frequency to lock the cavity, like say green and infrared at the same time. So it might be interesting to estimate if you have, for example, already an electric field in the cavity, what is the sensitivity when you generate another electric field due to magnetic conversion, whereas might be sensitive, let's say, to use this heterodyne technique where you have the beating between one frequency with the other. And it might be nice to have this done in some way to estimate the magnitude of a gravitational wave when you have already a resonant electromagnetic wave in the cavity. And, yeah.
Can I jump in?
That's
Sure.
gonna be number.
Yeah.
This is what tomorrow will be discussed by Raffaele.
And also Diego.
Yeah. In a sense, this is so. The question is whether we can just translate what you are doing, so to say, in our ALPS domain, and then.
Yes.
But to be completely clear, we're not doing a beating. So we have a loaded mode and an empty mode. So we look at how much signal goes in the empty mode. But I mean, it's a small generalization.
Yes, I have this experimental field in mind. So, and the other thing I have in mind that we can choose the polarization, I guess, of the gravitational wave produced in the cavity. So even if we have the same frequency, maybe orienting the magnetic field in some way, we can choose a polarization to be orthogonal to the other one. So, this wave that propagates maybe can generate rotation or ellipticity. It is worth to look all this experimental technique where, and what is the, let's say, the magnitude that translates in gravitational wave. So,
it's better to, I think, you could shape the cavity. I think some of the interesting thing is you can kind of shape the cavity to get one mode that is a bit more coupling with the wave. I think that would be, you see what I mean? Not spherical, not whatever. So something that really has the quadrupole.
Are you thinking in microwave? Because the cavities in optical, they are very different not so much different, but
yes, we are thinking about microwaves.
I know in microwave when it is not exactly as in the optical regime. In the optical regime, we have small things, small mirrors, and the tube is very long, so 120 meter with a radius of diameter of 50 millimeter. So this is
that calculation will not be in our talks. So
of course not. Yeah, but maybe so it would be interesting. You raise a good question. I think and this we have to think about that, and then we know now that other theorists which are working in this field, we can try to
it might be worth
try to understand that.
It might be worth to
investigate.
Maybe it is a little bit more sensitive rather than detect directly the field that is converted in, let's say, in dark. Maybe having the heterodyne technique can help. Okay, good.
Francesco? No, I think Fernando has asked a question.
Yes, thank you. No, just coming back to what you mentioned before, Andreas. If you want to have something in a big lab like DESI, dedicated just on the gravitational waves, what would be the procedure within the lab to try to reach to get an approval to have the dedicated experiment there?
I think the best thing is now Axel should answer that. So because I also follow it, but now there are new procedures. I mean,
So that's it's tough to say. So DESI is installing a new critical decision process at DESI for larger scale projects, where we then have to approve first committees, and then we get a C0, like you know from the US. It's similar strategy, but it's a formal thing. You only would like to enter this once you have a clear proposal, a clear collaboration, and then it makes sense to start this process. So DESI has now dared to engage in axioms, and we are constructing this infrastructure. So the next steps for me would be that we as a community come up with proposals, concrete proposals, what to do with this infrastructure, and only later maybe propose new infrastructure. But the first thing is, to my understanding, to convince also management at DESI that it's worthwhile to go for local experiments on campus. So let's say up to the size of this 250 meter Alps 2. Because you see that also many people are pushing for larger scale things, be it that DESI engages at accelerator experiments at Cern or in Japan, or DESI engages in Einstein. So we have this competing larger scale things. And to me, it appears that we have to communicate as wide as we can that there's also interest, physics interest, in this mid-scale experiments. Just to secure that not maybe someone decides or a committee decides that gravitational waves are interesting. Now DESI puts all its efforts into Einstein, and we close down Alps 2 once axion search is finished, just to free resources. This is somehow the things we have to balance. And I like this workshop very much because it is becoming more and more clear to me as a non-expert joining this workshop now, how important gravitational wave search is for particle physics. But this we have to communicate also at particle physics conferences, just to show what you can do in principle once we enter an experiment on this. And therefore, it's a delicate balance that we have to keep up options, but I think also too much strategy might be harmful, because then smaller scale initiatives might be damped, because everyone's only looking at the big strategies. But at present, we have to explore all these different options we have heard here. Just people have to get the opportunity to play around, test concepts, similar like Axiom some time ago. And then later strategy emerges with some kind of flagship projects maybe, but also supporting the smaller scale things. So in a nutshell, I think what we have to do now is to raise interest everywhere and the fascinating issues of this topic.
On a similar connection, do you think CERN involvement in one of these experiments would also boost the involvement of DESI, or do they complement each other?
No, I think we could very well team up with CERN.
Okay.
This is at least a mid-scale. And for example, this was also one of the successes that we get Baby-Axo now, because we were able to convince CERN to contribute the magnet. And just also from political grounds, if you, for example, for the axons, it was important, beyond ALPS 2, for the axons it was important to convince also DESI management we are that much interesting that even CERN contributes. This is a big political issue thing, DESI. And then things become much easier to build something.
That's good.
And certainly if it comes, for example, to this Jura, I think this was also on one of the slides, possible successor of ALPS 2 and axion research. Once you have to go to other dipole magnets, for example, with resolators, then CERN is the place to go, because we are using magnets from the 80s of last century. And the other proposal which was made in our discussion, just to think of presenting the high frequency gravitational wave physics opportunities to the PBC at CERN. I think this should be, we should follow up on this.
So you think that we can try as a community to reach them?
Yeah.
This might be a good outcome of this workshop, for instance. One of the outcomes.
Yeah.
Okay. Well,
by the way, at Cern, I guess some of you know, at Cern there is also a new roadmap, let's say, called Quantum at Cern, which is also not very well defined, but it's to use quantum technologies. I don't know, have you discussed this already? So
we didn't discuss it here. No.
Okay, so there is, sorry.
Oh, sorry. I was just going to say that maybe I can comment on that, but please go ahead. Later, I can make a comment.
All right. So it's a program by, well, it's a kind of direction that CERN was to get involved. It has 3 legs or 4: quantum information, quantum simulators, quantum metrology, and maybe another one. Well, I don't know. Anyways, the important one for us, I think, is quantum metrology. They are certainly trying to get into this business. They have, of course, a lot of expertise in certain things. The problem with this is it's a kind of soft program, as many times at CERN, because it's not purely on the main. But as far as I know, they are trying to look for things to do, right? So, and they, well, you know, in particular, Michael Doser, for those who know him, who is the head of the anti-hydrogen facilities. They have been quite experts on penny traps. I mean, things like cannot be exactly used to this, but also kind of resonate. They resonate with the idea of developing not only the PVC, but also this kind of other proposal that in the end, maybe for gravity waves may have an impact. So, yeah, Yvette, sorry.
Yeah, no, sorry that I was thought I was first muted, then no. Anyway, thank you, Diego. No, that I made like a little comment about that in the previous discussion, but maybe to raise it again. So the interest in that program that you're talking about had some connection with interest in the UK, as I mentioned before, that there was a program for funding, was called Quantum Technologies for Fundamental Physics, and there were things like atom interferometry to measure dark matter and dark energy, and well, so several different things. Like I said, I think I promised to send it, but maybe what I should do is put some of the websites on that on the other conversation platform that we have. And there was also a roadmap conference, and actually I participated on it because they invited all the projects that were funded. And then they had like a slot left, and they found my project interested, which didn't get funded, but I managed to participate on that. So, well, from the UK, there was a huge like interest on, everybody suddenly was interested in fundamental physics, all the quantum people. So that was kind of a really good exercise, but it's now floating. I mean, now there's a call that is, the deadline is in a few weeks. But for projects that have very little money, it's like 500K. So you can't really start a new experiment or anything like that. And I think the things that were funded were things that were already quite established, not new proposals like the ones we've been discussing here. But I think there's an opportunity also there to reach into that community. I also mentioned that to Fernando, that I've been talking to the people from the physical science and engineering from the founding agency here in the UK, saying like this would be very interested, especially because of these sort of gaps of experiments that there are for high energy physics and for gravitational waves that look, like quantum technologies could really help in that direction. And they were very positive, but if there's now a push from the sort of foundations, fundamental physics like what's it called here, STFC?
STFC.
Yeah, then that is kind of pushing from both sides, and that has already kind of an established connection with the people of high energy physics and Cern.
That's good.
Yeah, I'd like to get briefly back to the Qti initiative at Cern. So I did actually forward our conference announcement there. I don't know if we may even have somebody in the audience, if so they can speak up. But anyway, there was interest, and that's definitely, I mean, at least I think that's a connection we can quite easily and low level try to establish. So maybe what to do concretely is, if kind of the people who would be interested in exploring this, they could just shoot me an email. If they already know who they would like to maybe get in touch with, or kind of which subdivision of the QTI they would like to get in touch with, you can tell me. Otherwise, I'll try to figure out who is the right person here. But yeah, I mean, at least kind of at the level of just starting to talk to people, I think this is something we can quickly and easily establish.
If I may add up on this, there's soon a PBC technology subgroup meeting. And maybe we can just explore. I can forward this. Valerie, do you know about this? Otherwise, I can forward the link to you. And then we see whether this could be an option.
Yeah, please forward. I probably should know, but I don't.
So we are already touching the 3 o'clock, and I think we had long discussions. We can of course continue on Mattermost, but tomorrow we will also discuss the strategic things. I don't want to stop now all the discussions, but I think I think we got quite a nice picture meanwhile about what could be done with large-scale facilities, and yeah. So therefore, yeah, Marcel?
Andreas, if I may,
okay.
Because of this discussion, I think we might have see really concrete tasks. Yeah. So in context of ALPS 2, I would like to get in touch with experts to check whether our data recording is appropriate also gravitational waves, or do we have to record other things? So do we have to add up on the readout and just decide whether any search for transients is meaningful with ALPS 2?
Yes.
And for baby AXE, we could also set up a small group discussing with the baby AXE collaboration whether it's meaningful to look for some gravitational wave, microwave antennas at the far end of the magnets. So we could really come down to concrete detector work.
That would be, I think that would be a very good outcome. So how can we proceed? So should everybody who is interested in one of these things, he should contact you, and maybe you repeat this also tomorrow in the final discussion when we have more audience, because now we have only 27, And so I mean, I think that would be a very, very good outcome.
Yeah, I think
please feel free to
small working groups would be great. And I would also like to take this opportunity to ask for some help because there are several things I would like to do. And without people with your expertise, it's really hard. So for example, one of the things I would like to explore is the possibility of looking at the stochastic sources and so on, the signals. That would be great. And also sort of improve my work, taking into account your comments. And, you know, for example, I do know that I show some figure of merits that perhaps are not the ones that you're used to looking at. So putting it in a language that is more accessible to people in your field, that would be just like a nice starting point. So for example, when I give my precisions and stuff like this, I don't give them in the standard way that you look at them. So that would be very helpful. That's kind of a little thing to do, but then more of a project would be to look at other signals that I haven't looked at. And I sort of have an idea of how could we do that, but I'm not have that very clear. So a little group around that would also be something very positive for me as an outcome of the meeting.
Yeah, so I think what we could do very low level, I mean, I think like we should collect these ideas, right? And particularly these ideas where you say you need help by somebody who knows XYZ, right? Or you need help by somebody who is just, you know, willing to put time into learning XYZ. And then we have the mailing list, right? The mailing list, which, you know, contains kind of the people of this conference, the people of the previous conference, the people of the white paper, the people interested, right? I mean, there's big overlap between these groups. But like if kind of, I mean, maybe kind of at the end of the workshop, kind of you already walk out of here and you already have the 3 people you need to do this, right? But otherwise we can always, I think, just suggest kind of these type of projects via the mailing list and see if somebody, I will be surprised if nobody jumps on board, right? I mean, I would rather think you'll get too many replies and then you'll have to kind of deal with it, but
no, and there's a lot of work done already, so it's more like it's not very time consuming. I suppose from your side is more like giving a supervision and an orientation more than putting in like a hard work. I think we've put a lot already on things that they're already like in the drawer ready to come out, but need a little bit more things. No, I mean, well, like looking at other sources would be a bit more, but maybe not so time consuming.
So let's definitely keep that on the agenda for the discussion tomorrow when as one of the kind of concrete next steps that we can do.
Great, thanks.
Yes, very good. That was a good last word. So see you tomorrow morning, and have a nice evening or morning or whatever.
Bye now.
Bye.
Cheers.
Bye.